So in today's videos, we're going to talk about batteries, which is their common name. The technical name for these are voltaic cells or galvanic cells. And the thing to keep in mind is they run by spontaneous reactions. The free energy for the two half cells when they're combined together is less than zero, so it's negative. So what we're going to focus on in today's talk are four types of batteries. The lead acid battery, which is common found in vehicles that you may drive. Lithium polymer batteries, which are what drives your laptop and your cell phone. The alkaline batteries, which are the commonly disposable batteries that are used. And then the hydrogen fuel cell, which is battery of the future, just to present some ideas. And when you look at all these, I'd like you to practice taking your half cells and finding out the E cell, determining who's the undergoing reduction, who's undergoing oxidation. I'd like you to also find the overall equations for the batteries based on the half cells. And then at the end of this, we're going to look at some of the technical barriers or places that batteries need improvement, just to put some seeds in your head so you can think about how to make batteries better. Because once we solve how to make batteries better, we're going to solve a lot of our transportation and energy problems. So let's get started with the lead acid battery. And we're going to just jump right in and pull up the half cell reactions for this. And this is going to give you a great opportunity to just practice some skills you've already developed. If you'll look back on the early eChem videos in this YouTube channel, you'll see to combine half cell reactions to get the overall equation and how to determine the E cell. So this is a good opportunity, given these two half reactions, to determine where the anode is, where the cathode is, do the overall equation, and figure out the E cell. So at this point, let's just stop your video, practice. What I'd like for you to do is find the E cell for the battery. Also rearrange and solve for the overall equation, and when you're ready to check your work, you can restart the video. So let's see how you did. The first step is probably to determine that the higher reduction potential is associated with the species that undergoes reduction. So this half cell reaction is going to take place in the cathode, and then the lower voltage is associated with the half cell reaction that takes place in the anode. So the top reaction, as written, is what's going to take place in cathode. The bottom reaction will actually run in reverse and take place in the anode. So we'll flip that over. And then according to the equation you learned earlier, you can take the reduction potential minus the oxidation potential, which will automatically change the sign. You get an overall E cell of 2.01. When you cancel out common species, which if you look in here, you're going to have 3 protons on the reactant side here, but you'll cancel with one of the protons here. All the electrons should cancel, and that's one of the keys to knowing that you have the half cell reactions written in the same way as the electrons should cancel. When you collect all the terms, you end up with this overall equation, which basically says a lead 4 oxide is actually going to lead 2 sulfate, and then this lead 0 is actually going to lead 2. So in both cases, lead is changing state, and this is a good practice for you. So a few points that I would make about this lead acid battery is, first off, the anode builds up protons, but these are consumed in the cathode. So if you look at the reaction here, in the oxidation side, we're creating acid, which is going to change the charge balance and start to make the cell more positive as the reaction goes on. And in a very simplified battery, as we learned earlier, you need to compensate for this with the salt bridge so that the charge balance is maintained. But in the battery design, someone's figured out how these protons could be consumed over in the other half cell, and hence whatever positive charge being built up here is being consumed over here, and then as this reacts, it has a no net charge in the products. So that's kind of one of the ongoing themes you're going to see in all these batteries, that there's a way to consume positive charge or negative charge buildup by using it over in the other compartment, and this alleviates the need for the salt bridge. So here's a diagram of that happening in the battery itself. And the key to this lead acid battery working is that the electrode compartments are actually just separated by space. They don't actually literally have to be in a different compartment. Then this inner solution is just full of sulfuric acid. And as you study the half-cell reactions, that's not as obvious, because here's one equivalent of hydrogen sulfate and 3 equivalents of protons, but that doesn't really make sense as far as coming from sulfuric acid, because we're missing a couple protons. But if you go down to the overall reaction, it all works out and it balances. And that's generally the take-home for these sorts of things. When you get to the overall balanced equation, this is a better equation to use for stoichiometry and to know the amounts of material present than the half-cell reactions, which really are pertinent to figure out voltages and which species is undergoing oxidation, which is undergoing reduction. Notice the other part about this lead-acid battery is that the reactants of the products are both solid, so the electrodes stay in place. So for example, if we go up here to the cathode side of things, you can see that lead oxide is a solid material, and as it converts over to lead 2 sulfate, it is also a solid material. So the lead doesn't just flake off and go into the solution like we saw in, say, for example, in the copper electrode or the simple electrode we've studied prior in previous studies. So this is the key to making it rechargeable is you can't have electrode materials going into aqueous or gaseous state and leaving, or else you'd have a heck of a time trying to recharge the battery and have the electrode, especially in an active electrode like this, where it didn't flake off. Look on the other side, on the oxide or the oxidation side, the anode side. It's the same thing. Lead solid turns into lead 2 sulfate, which is also solid, so it doesn't change position. The other thing, just to make you think about it, because a lot of you are familiar that your car uses 12 volts, and this, as you calculate, is about a 2-volt battery. So you might ask yourself the question, well, how does it get the voltage it needs? Actually, this is one individual cell at 2 volts, so you would need 6 of these cells wired together in series to acquire the appropriate 12-volt potential. And yes, this battery is rechargeable. In essence, as you run the reaction forward, these species are all going to lead sulfate and water, and then when you run the reaction in reverse, it's going to regenerate the dissociated sulfuric acid, the lead, and the lead oxide electrodes. And this is has led to the longevity of the battery. It's just that this is pretty bulletproof. Battery continues to be rechargeable, and you can refer to just how long you had the same battery in your own car to understand this, and considering the fact that every day it recharges every time you turn it on. Okay, the next battery we're going to study is the LiPo battery, or the lithium polymer battery, which is commonly found in computers and cell phones. And the two half reactions that I would like for you to be familiarized with and are shown here. And so once again, let's do some practice. Why don't you look at these two equations, stop your video, see if you can determine which equation would take place at the anode, which would take place at the cathode, figure out the E cell, and then stack the equations together and figure out the overall equation. And when you're ready, you can restart the video and check your work. Well, let's see how you did. So by looking at the voltage, you can determine that cobalt 4 oxide turning into the cobalt lithium oxide is what's going to take place at the cathode. And so the other equation would need to flip in order to get the balanced overall equation, and that would change the sign, and then it would be 0.7 minus a minus 3 volts, which in essence adds together and gives you a 3.7 volt battery. So now let's study this battery a little bit. When you study this reaction that you can see takes place at the anode, you can see that there's a lithium graphite complex, which is shown here, and the the graphite is basically these phenyl rings, these carbon rings that are locked together in a structure, and those have the ability to bind lithium in their basically they're physical pockets that bind lithium. And under potential, they're actually able to release lithium by first oxidizing it, which ejects it. And then, as you could think back to using salt bridges, prior the material was neutral, then you make the lithium ion, so it's starting to build up positive charge, which would not fly unless you had a salt bridge, and we're providing some sort of negative charge to counterbalance that. But in this particular reaction, this migrates over to the cathode side, and then it's consumed by cobalt-4 oxide and makes this cobalt lithium oxide. So it's basically cobalt-4 going to cobalt-3, and that is how you prevent charge buildup. Again, the products and the reactants are in the solid state, so they're not moving around. The only thing that's moving is the lithium ion, which is created, and then consequently that has to migrate across. In this case, compartments really are separated from each other, and the key to this technology is having a membrane that can selectively pass lithium through. But if you look on your periodic table, you can see the size of lithium as a cation. It's one of the smallest cations there is, except for hydrogen. So that can be a physical barrier that can actually allow lithium plus ions to go through because they're so small. The key to this technology is understanding physically how to make that membrane. The diffusion through that membrane is actually one of the rate determining steps as far as how fast this battery is able to operate. This is rechargeable. You can kind of understand that from the overall equation. If you have cobalt-4 oxide and lithium 0 in a graphite encapsulation, and as you free up the lithium plus and it flows over and makes this cobalt lithium oxide and the free graphite. If you go in reverse, the lithium ion, and this is probably easier to see in the picture, if you go in reverse, this lithium ion just flows back through the membrane and reloads as it is reduced back to lithium 0. So in this next battery, we're going to look at the alkaline battery, which is common batteries we use and throw away that we find in our calculators or flashlights, that sort of thing. So we're going to start by looking at the half reactions, which run the show. And once again, this is going to be a good chance for you to practice your skills. I'd like for you at this time to stop the video, see if you can determine which half reaction is going to take place at the anode, which is going to take place at the cathode. Solve for the E cell, and then also rearrange the equation and solve for the overall equation for this cell. And this is a good chance for you to look at the electrons that are transferred in both half reactions, or they don't match. So it's a good chance to use that skill where you multiply through one reaction and see how it affects the overall reaction. So when you're done practicing this, you can restart the video and check your work. So let's see how you did. You can see by looking that the higher voltage reaction is the manganese 4 oxide turning into this manganese oxide hydroxide material. So it's basically manganese 4 going to manganese 3, and then the other reaction going to take place at the anode. And so if you're trying to solve for the overall equation, you would flip this reaction. So when you're solving this particular reaction, you can see that you have to multiply through by 2 in order to balance out the electrons. So as you do that, it's also a good reminder that the voltage doesn't change. That is taken care of in other calculations that you do in electrochemistry. You solve for the overall equation. The battery itself is a 1.50 volt battery. And if you'll pull open your calculator and look at your batteries, you can see that AA and AAAs are 1.5 volts. So therefore, one of these cells will take care of the voltage that's required. You don't have multiple cells in series like you do with the car batteries. So let's look at this particular cell. So one of the things that happens is the manganese 4 oxide turning into the manganese oxide hydroxide. That reaction itself doesn't have anything that conducts electricity, so you have to have a inactive electrode, and usually that's carbon, and really what you have to have is a carbon mesh with this particular reaction kind of interdispersed in there to pick up the electrons. And as this reaction takes place, it creates hydroxide ions, which would of course be a problem because you're building up negative charge. So to alleviate the salt bridge, this hydroxide is transferred over to the half cell where oxidation has taken place, and is consumed by the zinc, becoming zinc 2 hydroxide. So one of the keys to this is just basically having a membrane in here that's able to selectively transfer hydroxide. This particular battery is very well sealed. You can't have impurities that'll do acid-base chemistry with this hydroxide. And again, the reactants and products are all solid. The question quite often comes up, hey, why isn't this rechargeable? Because I can look and see this, that manganese 4 oxide, it's solid. It's making this manganese oxide hydroxide. It's also solid. I have zinc solid turning into zinc 2 hydroxide, which is also solid. So kind of from our model, you would think that if the electrodes aren't really changing form and leaching off into the electrode solution then, or becoming gaseous, you should be able to reverse this reaction. And to some small extent, these are rechargeable, but that it has a very limited lifetime, and quite often it overheats, and kind of the battery could be in danger of exploding. But my look into the research of why this happens is it really is about its solid state, and that's back to the crystalline state, which we studied in General Chemistry 2 in the very, very first sections where we looked at X-ray crystallography. And actually, manganese 4 oxide could have very different forms, and chemically they're the same material, but their physical crystal structure has a different configuration, and one of those is not as conducive to undergoing this chemical reaction as we have it drawn here. So consequently, from what I understand, the favored form, the gamma form, doesn't return that, but returns to a different, less electroactive form physically when it gets converted. So I guess if I was trying to hand-waving explain this, it would basically be that manganese dioxide does not return to its original form because there's a more favored path, and I don't know whether that's kinetic or thermodynamic favored, but there's a more favored path to a different species when you try to recharge the battery. Now again, the key to this is the membrane that selectively transfers hydroxide ions, and again, the rate at which this hydroxide ion moves over to the zinc side is one of the rate determining steps here. This is non-rechargeable. And the last battery that we'd like to look at is the hydrogen fuel cell. Again, I'm going to show you the half reactions. I'd like for you to stop the video and practice determining which reaction is associated with the anode, which is associated with the cathode. Try and rearrange the equation, get the overall equation, figure out the E cell. So stop your video. When you're ready to check all your work, you can restart. Let's check your work. Obviously, the protons turning into hydrogen gas is the lower voltage, so that's where oxidation or what takes place at the anode. The oxygen reaction is what takes place at the cathode. And let's study this particular cell. But first, again, we have an imbalance of electrons, so we have to multiply through, get the electrons right. And again, that doesn't change the voltage, although it was 0 volts. And just a reminder again that doesn't mean that it's the absence of voltage. It just means that this particular reaction is our reference, which we call 0 volts. It is some voltage. There's some below it, some above it, but we just chose to use this as the standard 0 voltage for aqueous solutions. Some other standards that are often used are mercury reaction and also silver 1 reaction. Get the electrons right, you solve your equation, you end up getting a voltage of 1.23 volts. The overall reaction is, in essence, the burning of hydrogen. Hydrogen and oxygen makes water. It's the same thing that would use if you just ignited hydrogen. Again, the anode is building up protons, which would lead to a buildup of positive charge, but these are transferred through a membrane where they are reacted with oxygen, forming water. This is a fill cell, so we're building up products, in this case water, and it's actually water vapor, which would cause problems if this was a sealed cell that we were trying to run to completion and then recharge, because you'd be building up all this steam pressure. But this can actually just be ejected, and you just keep feeding this fuel as long as you have hydrogen being fed to the anode and you have oxygen being fed to the cathode and water being ejected from the cell, then this basically keeps flowing in one direction, creating 1.23 volts. One of the keys to this technology is the fact that you are transferring the protons, and again, this is a proton selective membrane. We've already developed that for pH probes, and again, it's easy enough to think about when you consider the size of a proton. It's one of the smallest molecules, in essence, consisting of a proton, so physically it's easy to make a pore that's size selective for protons. And one of the things that's not drawn in here per se is that these require some sort of inactive electrode to pick up the charge. Hydrogen doesn't transfer electricity, nor does oxygen gas. So usually these have inactive platinum electrodes, and this is quite handy because platinum is known to actually catalyze these two half-cell reactions. So as we know from earlier in this chemistry, we've learned how catalysts work, and in this particular case, platinum binds hydrogen and starts to weaken the hydrogen-hydrogen bond. This cell is non-rechargeable, but then again, it's a fuel cell. And the interest in this is just that the fact that it basically is, as I stated earlier, it really is just the combustion of hydrogen and oxygen. But the beauty of using electrical energy, say, to create motion as opposed to just burning hydrogen in a combustion engine is that it's a lot more efficient. The combustion engines tend to be in the range of 30 to at best 40% efficient, whereas batteries can transfer in electrical engine form into motion with up to 70% efficiency. So that's the advantage there. So just kind of, I've mentioned on some of these things, but I wanted to really put them in as keys to battery improvement, and helping you understand how batteries work and kind of get your mind thinking about some of the keys to making a battery work. But in many rechargeable batteries, the key to repeatable cycles is the absence of impurities. So the cells have to be sealed. So some of the technology that needs to continue to be developed is ways to purify cells. Just for example, if you look back in the lithium polymer battery, the lithium ion is a material that can get transferred. And this you might think could happen through an aqueous system, but these cells would get hot enough that it'd be very easy to create steam, and the cells would build up steam pressure. So they put them in dimethyl carbamate, which is a material that has a really low vapor pressure. And this is the next comment I make about sealed cells. Power density is determined by how many electrical events are in intimate contact with the electrode at any time. So if you look at any one of these half-cell reactions and you think about it creating 1 or 2 electrons, Those are the electrons that flow through the circuit to create the battery. So if you're thinking about amperage that's flowing at any given time with a given voltage, you actually have to have electrons available to create the amperage you're calling for. So the more of these events that are in contact with the electrode, the more able for this reaction to happen and basically put electrons on the wire. And so it really is a surface area event. And basically the higher surface area electrode is the key to increasing power density. For example, in the hydrogen fuel cell, you might have a platinum mesh. The higher surface area, the more hydrogen turning into water reactions, or hydrogen turning into proton reactions can take place, or oxygen turning into water, the more those that can actually take place and touch the electrode. Electrochemistry is under kinetic control. There's implications for this. If these batteries move down to lower temperatures, then the chemistry, the reaction is going to slow down, and therefore it's harder to create as many electrons, and that's why, for example, an alkaline battery may not work well below freezing. But conversely, that same theory can be applied if you want to lengthen the life of your battery. You might throw them in the refrigerator and slow down any kind of slow leak that's occurring. And if the technology is good, they may not leak anyway, and that's kind of one of the shticks that you'll hear on a lot of batteries. They have a long lifetime. Being able to use the products in one half cells, the reactants in the opposite, is what alleviates the salt bridge. But then again, the factor, and this is still true with the salt bridge, the factor of how fast those particular ions are transferred from one compartment over to the next, from the anode over to the cathode or vice versa. That's under diffusion control, which creates another kind of bottleneck as far as how fast this battery can operate and how much charge density it carries. So, thinking ahead to how batteries can be improved, the rate at which those species can move from one cell to the other, the faster you can get that, the higher performance your battery can be. So I hope I've taught you a little bit about batteries, some of the general designs of the batteries that you are familiar with and that you use in everyday life. Maybe tweaked your thinking a little bit about how you can improve batteries, things that people are working on in research and that you yourself may work on in the future. And also gave you a little bit of practice in doing your E-cells and your overall balanced reactions.